Hey guys, so this is going to be a bit of a little more complicated question. This is about year 11 calculus, advanced maths sort of level for HSC. This would be the sort of question you'd get if you were taking an exam and it was maybe a 2 or 3 marker. Um, okay, let's run through it. Given a circle with a radius of 6 centimeters, so a circle with radius 6 centimeters, find the dimensions of the largest rectangle that can be inscribed. Okay, so what does that mean? What does inscribed mean? That means we can fit inside. So I'm actually going to get rid of that radius. We'll just keep in mind that it has a radius of 6. Um, Now, if we have a rectangle, we could get something like that, although that wouldn't have much area. Um, so we probably don't want it to be very tall and very skinny. Similarly, we don't want it to be not that tall and super wide because that's not much area either. Okay, so let's pretend that's the center. Um, so neither of those seem to be the best way of going about that. So going about constructing that rectangle. What you could imagine is maybe the rectangle probably should look something like that, right? Something like that. Maybe a little more wider or something, but that definitely has more area than just this little slice here or just this little slice here. Okay, so what do we know? We know it has a radius of 6 centimeters, and that's the only number that we've been given. So how do we tackle this? There's actually 2 ways to do it. So we're going to run through the calculus way first because that's the topic that they'd be testing. And then we'll try to do it a bit more intuitively and see if we can make a simpler approach. So how the question's usually given is they maybe give you a diagram or you have to draw it yourself. But what you should notice is rather than drawing the radius of 6 here or drawing the radius of 6 here, it's that you can draw the radius of 6 here, right? Because what's a radius? It's just a distance from the center to the circumference of a circle, right? So we could draw it there and that'd still be 6 centimeters. I'm going to talk about why that's useful in a second. Okay, so if we're trying to do a um, maxima and minima question for calculus, how do we start? Well, we start by defining an equation. Often it has 2 or more variables. Defining an equation for the thing that we're trying to maximize. So what are we trying to maximize? We want to find the dimensions of the largest rectangle. So we want to maximize area because that's what they've defined as the largest rectangle. So let's write an area equation. So we have area, and how do you find the area of a rectangle? Well, you do base times height, right? So we'll call this B and call this H. And so you'd have B times H, right? It doesn't matter what letters, you could use X and Y if you'd like. Okay, now what would be the next step? We would probably want to differentiate. We would like to differentiate, but we can't do that because our calculus only lets us differentiate single variables equations. So we need to kind of get rid of one variable, and this kind of introduces the idea of simultaneous equations. If you take a look at this, the reason we've constructed it like this is we could also say that this is 6 centimeters, right? So we get a distance of 12 centimeters there. And we know it's a rectangle, so that's a right angle triangle. And so what you can do from that is you can construct that h squared plus b squared equals 12 squared, which is 144. And that comes from our good friend Pythagoras. So what we'll do there is solve for a variable. So we can pick b or h. I'm going to go with h. I'm going to skip a couple of steps. We're going to move the b squared over and then square root both sides, right? So we're going to get 144 minus b squared. Okay, why is this useful? Well, now I found an equation, I'll call it equation 2, call that equation 1, that describes the variable h, but in terms of b, meaning I can replace my variable h with something about b. So knowing that, I'm going to sub equation 2 into equation 1. Let's just switch colors because it's getting a little too green. And we're going to get something like a equals b times, and we put this in there instead of h. square root of 144 minus b squared. Now if you look at it, you just have area as a function of the base. So given the base, you could now find the area. Okay, so how do we maximize? Well, the first step to maximizing something is to differentiate. So we're going to get a dash or dA dB. And we're going to have to use the product and the chain rule here. So let's use product rule. So product rule says if you've got two things multiplied, you take the derivative of the first one, which is just 1, and times it by the whole second term. So we just get 144 minus b squared, and that needs to go all the way over, plus the first one by itself, first term normally, so just b, times the derivative of the second thing. So the derivative of this is a little more complicated because you've got to use chain rule on it. So what's going to happen is you're going to bring down the power. Now, if you remember carefully that with indice rules, a square root is the same as a power of a half, right? So we can bring down that half, then multiply by the derivative of the inside, which is negative 2b, and then take 1 from the power. So what'll end up happening is you'll get a negative half, and a negative indice just means move it to the bottom. Well, move it to the opposite side of where it is. Okay, so how do we simplify this? So we're going to get, yep, so 144 minus b squared. And then let's take a look at this. So we're going to cancel this 2 with this 2. B's are they're going to multiply, so we're going to get b squared, and this negative, we can move it out the front, right? So we're going to get negative b squared all over 144 minus b squared. Right, so that's your a dash. Let's loop up to here. So how do we find the maximum? This is just the derivative. Well, max is found when the derivative equals 0. Now, why is that true? Let's think about what the derivative means. It means that you are finding, another word for the derivative is the gradient function, right? What does that mean? It means it's a machine or a function that tells you the gradient at any point on the curve. So this equation here, this thing that we found, is our gradient function. So if we put in a b value of 0, we get 12 minus 0, so you'd get a gradient or a steepness of 12. Okay. Now, what do we want for a maximum? Like if we want the curve to be at a maximum, how steep would we want it to be? 0, right? We want it to be 0. So the max is found when the steepness is 0. Okay. So right. So knowing that, we don't need to really do that right now. We just need to kind of assume that it's true, but understanding is good. So derivative is 0. So we set this equal to 0 instead. So, right? So 0 equals, I'll write it one more time. 144 minus b squared on 144 minus b squared. The reason I didn't simplify when I usually would before I do other things, I would have simplified this, is because I know I'm going to set it to 0. Now watch what happens when I set it to 0. I can multiply everything by this denominator, right? Because currently I have two things. This has a denominator of 1. It's not there, so it has a denominator of 1. And this has some other denominator. So we'd have to kind of add fractions, right? But instead, if I multiply by the denominator, we'll see what happens. If I multiply this side by the denominator, it's still going to be 0, right? It's not going to change. 0 times anything, no matter what it is still 0. What if I times this by the denominator? Well, they're the same thing, so I'm just going to get this thing squared. If I square this, what happens to the square root? It'll disappear. So I'm going to get 144 minus b squared. And if I times this by the denominator will cancel with what I times by, so I'll just get minus b squared. So as a result, I have a very simple equation with one variable. So I'm going to collect the like terms and move it to the left. I'll get 2b squared equals 144, b squared equals 72, and b equals root 72. So now we know the length of the base that would give us the maximum area of the rectangle. Note we're trying to find the dimensions, right? That's what we're looking for. We're trying to find the dimensions. So this is only part of the solution. Okay. All we have to do is find the other dimension. So what is h? And the question is, what is h? Oops. Question mark. right? What is h? Well, go back to equation 2, and we'll see we made h the subject depending on b, and now we know b. So what we have to do is sub b into that equation, into equation 2, right? So we're going to get root 144 minus b squared, and squaring the root once again gets rid of the root, so you just get 72. If you do that, you get coincidentally the same value, or maybe not so coincidentally. So the two solutions, the two dimensions, are root 72 and root 72, and they will give us the maximum area of the rectangle. Okay, so let's really quickly, hopefully that made a lot of sense. I think the derivative would be the most difficult part. You need to make sure you didn't make any mistakes there because it's product rule and chain rule. Okay, what we're going to do really quickly is we're also going to try and approach it a little more intuitively, so no calculus. It's kind of based on the ideas of calculus though, so I guess you still kind of need it. It's more ideas than straight maths though. Okay, so it's a tiny bit of a shortcut, but it requires a little bit of thinking. So what we need to notice is this idea here, that when you have a slim rectangle, you don't get too much area. And when you have a very wide rectangle, you don't get much area either. This comes from the idea that if you have two numbers, let's take an example, we need to have two numbers that add up to 50. Okay, so what are some possible ones? We could have 1 and we could do maybe not 1. We'll do that later. We'll do something like 20 and 30, right? These things add up to 50. Okay, so let's see what happens when we multiply them. We get 600, fairly large. Let's see what happens if we change these numbers. Still add up to 50 though. So 10 and 40, right? They still add up to 50. And we multiply those, we get a smaller number. What if we go even smaller? Hopefully we find the same trend, right? We go down, oh, that's not true. 49, I should just, yep, so 1 plus 49 is 50. So let's see what the product gives us. It just gives us 49, obviously. And so what we notice is as these two numbers get further and further away from each other, right? 20 and 30 are kind of close. 10 and 40 are further away, and 149 are very far away. The product gets smaller and smaller. So we could hopefully see the same trend if we got closer. So let's say the numbers won't be so nice, but let's say 22 and 28, right? I'm going to whip out my calculator to do that. 22 and 28. We get 616, so we get a little larger, which is good because these numbers got closer together, right? We got closer than these, so the number gets bigger than 600. So what we notice with a bit of pattern recognition is the closer the numbers, the greater the product, right? Closer numbers, the greater the product. Right, closer numbers, the greater the product. So the problem is then becomes, how close can I make the numbers, the two numbers? Well, the closest you can make it is 25 and 25, right? Those two numbers add to 50. So what do they multiply to? Well, that's just a square, so it's 625. Okay, and that'll be your maximum two numbers that you can multiply, the maximum of two numbers that you can multiply that also sum to 50. That's a whole question in itself. You could have done calculus on that as well to figure that out, but I think logic comes a little nicer. Okay, so why is that useful here? Well, we should be careful and notice what I said with my words. We said that the square, if possible, seems to be, which is always possible, sorry, the square seems to be the largest value when the numbers are the same, so they make a square. Well then, what shape would that be? If you take a rectangle, you could make it into a square. So if you make an assumption that this is true always, which it is, and you can go test that out for yourself, then you don't have to put b and h in here, and you can skip all that. That's what the calculus tells you. Instead, you can reduce the problem. Let's do it in blue, dark blue. You can reduce the problem to just being, we have a square inside a circle, right? So we call it x and x, and it has a hypotenuse of 12. And so keep in mind, we've done all the maximizing through the idea that a square is the greatest area of a rectangle. So from there, we can just go 144 equals x squared plus x squared, once again with Pythagoras. That'll give us that 2x squared equals 144, and x squared equals 72, x equals the square root of 72, which is what we had before. And so we'll find that since x equals root 72, which is this x maybe, but we don't have b and h like last time, they're both x. So we get root 72, which is exactly what we got. So the dimensions are, dimensions are root 72 and root 72, right? Exact same solutions we got doing the calculus method. This skips a little because it uses the idea of calculus that it's maximized, and this idea that it maximizes the area given that you have a square between two numbers. Okay, so hopefully that was a little interesting. You might see that question floating around in your upcoming tests, maybe if you're doing year 11 maths or year 12 maths. Wish you the best of luck.